Hey, welcome back to Abstract Algebra. In this, our second video lecture in section 4.3, we're going to be taking a look at the ring theoretic version of factor groups. So in this video lecture, you can see the goals are written there in front of you. What I want to do is show you that if you take an ideal in a ring, the factor group, which already exists, we know because that's a normal subgroup, and this abelian group is in fact a ring. So that's going to be the contents of theorem 4.32. And then I want to prove the analog of the first homomorphism theorem for rings. That's theorem 4.33. And then we'll look at a couple of examples. It sounds like a daunting task as we set out here, but it's really going to go pretty smoothly because a lot of the heavy lifting is already done in our group theory. Given this ideal, we know it's a subgroup. R is an abelian group, so every subgroup is normal. We already know that this set of cosets is a group under coset addition and so on. So we really just kind of have to plug some holes about the multiplication. The proofs are going to go pretty smooth. As we move through this, I've written out long statements of theorems. They're kind of complicated sounding, but we'll write the proofs together as we go. Okay, so let's just get to work. Here you're looking at the statement of theorem 4.32. Again, it looks pretty intimidating. It's got a lot of hypothesis, but let's just kind of try to walk through it. So the ingredients of it are you give me an ideal in a ring R. Okay, I've already mentioned, I'll write some of this down, but that ideal is a normal subgroup. So I can talk about the factor group R over K, and that factor group already has an operation called coset addition that we know is well defined. So one of the things this theorem is saying is that coset multiplication, the multiplication operation defined by taking two cosets and multiplying their representatives, that's also well defined. And in fact, that makes that a set of cosets, R over K, a ring. That's part of what the theorem says. Remember our old friend, the canonical group homomorphism, eta, that sends an element to its coset? Well, that's going to be an onto ring homomorphism, and its kernel's not going to change. Okay, so that's the statement of this theorem. Most of the work is kind of done. Let me see if I can kind of pace you through some of the details. So let's have an ideal called K. I'm just going to start trying to write down some of the stuff I just said. Let me let you look at that theorem statement as long as we can. So first of all, K is a normal subgroup of R under addition because R is abelian. Every subgroup of an abelian group is normal. So the set of cosets R over K is a group. It's an abelian group. So we don't have to worry. So that's the first ring axiom, right? We've got an abelian group called R over K. This operation, I'll highlight it. Coset multiplication has been defined, so we need to show that operation is associative. It's defined in terms of an operation that is itself associative. Maybe that's all I need to say. But first, we need to show that it's well defined. We need to show that if you multiply two cosets like that, that the answer isn't going to depend on the representatives, but rather just the class, because that doesn't follow from the additive structure. So that's some actual work that we have to do, okay? So let's take two cosets. Actually, we need to take four cosets. So to show coset multiplication is well defined, let's let, say, A, B, you know me, alpha and beta be four elements of this ring. And let's suppose that, say, the coset containing A is the coset containing alpha, and the coset containing B is the coset containing beta. All right? We need to show that the coset containing AB and the coset containing alpha beta are the same. Okay, so let's unwind what we mean here. If the coset containing A is equal to the coset containing B, well, that's true actually if and only if, I'll write this out in careful notation, the inverse of alpha in the group R combined with A belongs to K, right? So that's if and only if A is equal to alpha plus, say, little k1, where little k1 is in K. Sorry about running out of room, but I'm just going to write that down here. Little k1 belongs to K. Similarly, skipping the steps, I'm going to say, okay, well, if B and beta represent the same coset, that's going to be true if and only if B is equal to beta plus something I'll call little k2, and I know little k2 is in K. All right, so you know what we're going to do next. I've got an expression for little a, I've got an expression for little b. I'm thinking about a times b. Let's multiply them. Okay, so a times b. Replacing what we've got, alpha plus k1, beta plus k2. And like we talked about in class, in a ring, I can use the usual distributive laws to expand this thing out. I just don't want to commute elements. So if you see me take things out of order left to right, blow the whistle. But I've got alpha times beta. I'm going to get something that looks like alpha times k2. I'm going to get something that looks like k1 times beta. And I'm going to get something that looks like k1 times k2. The usual binomial expansion. Okay, and I'm going to rewrite this equation. Oops, I'm just about out of room. This proof better wrap up soon. So I've got AB minus alpha beta is equal to alpha K2 plus K1 beta plus K1 K2. All right. Let's look at these things kind of one product at a time. Alpha times K2. That's an element of K, the ideal, capital K, because little k2 is, and ideals are sticky. If one of the two factors is in an ideal, then the product is. Same for K, oh, sorry, that was supposed to say K1. Same for K1 times beta. That's an element of K because K1 is. K1 times K2 is an element of K, well, because both of them are. So in particular, as long as one of them is. And K being an additive subgroup, when you add three elements of K together, you get an element of K. All right, so what does that show? I'm gonna have to make some more space here. What does that show? That shows that AB's coset is the same as alpha beta's coset. Right, so this multiplication is well defined. Good. Here, let me sort of try to move some of this stuff up. I wasted a little bit of room. Oh, I can't move it across to page break. Okay, well, let's go back up to the statement of the theorem and see what we've done here. So I'll underline kind of what we're supposed to have proved. So we're supposed to show that this thing is a ring. And so far, I've just shown that the operation that we've defined in terms of multiplication is well defined. All right. Well, so what do I owe you? I owe you the associative law for multiplication, and I owe you the distributive law. At the end of the day, how would we be carrying out all of those operations? We'd be carrying them out in terms of operations in the ring R, where all of those properties hold. So I'm actually not going to write it out this time. I am just going to say that the associative law and the distributive law, they follow because they hold in R. Once we know that this operation of coset multiplication is well defined, the rest of that stuff is just tedium to write it down. It's all going to go through. For that matter, to say that this canonical map is a ring homomorphism, and it's onto with kernel K, well, the kernel of a ring homomorphism is the same as the kernel of it as a group homomorphism. So our work in group theory tells us the kernel of that map is K. That map was onto, just because the domain and codomain have more structure, it's not going to change that. So the map is still onto. So we really just have to use the multiplicative property of the, or we just have to show rather that this canonical map sends products to products. But you can almost see it here. I ran out of room below, so I'm going to do this like this. I'm going to erase some of my highlighting and colors, and I'm just going to point out to you that the right-hand side of this equation that we've shown is well defined, it equals eta of AB. Eta of AB is the coset containing AB. And likewise, the left-hand side of that equation, equals eta of A times eta of B. This coset multiplication is cooked up to make eta a ring homomorphism. All right, so really the heart of theorem 4.32. In graduate school, if I were a graduate school professor, I would have just said, well, we just need to show that this operation of multiplication is well defined. The rest of it is trivial. I've tried to kind of explain to you that the rest of it sort of follows from everything we've already done. Once we know this thing was well defined, we were done. All right, so we can talk about this in class, but for purposes of this video and the fact that I ran out of room, I am going to come down here and find the end of my proof and say we have proven theorem 4.32. All right, so that factor group construction, short version of it, if R is a ring and K is an ideal, it makes the thing a ring. And I should have made a comment while we were doing it. Do you see that ideal was precisely what we needed to be true to make that thing well defined, because one of these two factors is in the K, but the other one isn't. So we need something more than closure. We need that as long as one of the two factors is in there, then the product is. So an ideal is precisely the kind of object we need to make the factor group have the structure of a ring. Cool. All right. Here's a little bit more terminology. It should seem pretty familiar. A bijective ring homomorphism is going to be called an isomorphism, a ring isomorphism. We'll say that R is isomorphic to R prime if there's a ring isomorphism between them, and we'll use the same notation. We'll write R squiggle equals R prime, all right? Here's a little quick example. We haven't had many examples of ring homomorphisms. They're a little bit harder to come by, frankly, than group homomorphisms are. But let's take a look at this example. I claim that the map from C to C, given by Z goes to Z bar, you remember, maybe I should recall for you. Recall for you that if Z is equal to A plus BI, its complex conjugate Z bar is A minus BI. All right, so I'm claiming that this is a isomorphism from C to itself. So just to quickly sketch the proof of that. First of all, we'd have to prove that if we take two complex numbers, Z and W, we need to prove that this function is additive. So let's take a look. Phi of Z plus W, well, it's Z plus W bar. Yeah, and back in our work in the complex number section, we proved that Z plus W bar is Z bar plus W bar. That's exactly that property of conjugates. Just says that this map is an additive group homomorphism. That's what that property is. Maybe you're starting to notice that all these properties that you learned in courses where you studied complex numbers or matrices, they all turn out to be the reason that something is a homomorphism. Well, from our now sophisticated point of view, the reason you were taught those properties is because they're all homomorphisms. And for some reason, we didn't want to, when you were young and I guess fragile, we didn't want to pronounce words like homomorphism in front of you. But all of those properties that you learned, they were the algebraic essence of what you were studying. Okay, that's my little sermon. So let's continue on here. We need to check the product. Phi of Z times W, well, that's Z times W bar. And again, back in our work in complex numbers, the conjugate, that's why we study it. It's also multiplicative. So that shows that this thing is a ring homomorphism. It's a ring homomorphism. Okay, so what's remaining? We just have to show it's bijective. If we're claiming that it's a ring isomorphism, then it has to be 1-to-1 and onto. Okay, well, if phi of Z is equal to phi of W, that's true if and only if Z bar is W bar. But by the way you take complex conjugates, when you take a complex conjugate, you just negate the imaginary part. So if Z bar and W bar are the same, then they have the same real part and the same imaginary part. The only way that could work is if Z is equal to W. So phi is 1 to 1. And I'm almost out of room again. I never planned this very well. 1, 2, 1. Why is it onto? Can you finish while I'm trying to make this look nicer? It's onto because if you take the conjugate of the conjugate, you get Z back. All right. So you have a 1 to 1 onto ring homomorphism. You have an isomorphism. So it's kind of interesting. C is isomorphic to itself via this conjugation map, which you can really just think of as a reflection in the x-axis if you like to think of things as geometry. You can ask me about that in class maybe. Okay, so this video is getting a little bit long. I know this looks like a long theorem, but I'm going to kind of do the same thing to you. I'm going to try to convince you that all of our work here is done in this first homomorphism theorem. So let me just read it. It says if you take an onto ring homomorphism with kernel K, you can read it yourself, but I'll read it to you. Then the map from the factor ring, we can call it now, that sends a coset to phi of A is a well-defined ring isomorphism, and it's going to factor through the canonical map eta. So this usual diagram that we have, given phi, and it's on to R prime, if K is its kernel, then the factor ring R over K is always isomorphic to R prime, and it's isomorphic by this very explicit map. Okay, so we don't have to do a lot of heavy lifting to prove this. Everything is done in group theory. Group theory tells us, for example, that this function, psi, is well-defined. We don't have to prove that it's well-defined again. We know that it's 1 to 1 and onto, and that it's an additive map. We know it's an additive group homomorphism. Yeah, we already know that this equation holds for that. If you just look at this theorem and forget that R is a ring, and only remember that it's an abelian group, everything I'm highlighting is true. Right? We all know that. It's a 1 to 1 onto group homomorphism. So the only thing we need to show, that psi is multiplicative. What do I mean by that? I mean that psi of a product is the product of the size, and it's cooked up to work because psi is defined in terms of phi. So if we take psi of, say, the coset containing A times the coset containing B, well, that's psi of the coset containing AB, right? That's by definition phi of AB, which is phi of A times phi of B. You can pause and finish this yourself. That's psi of the coset containing A times psi of the coset containing B, right? So the rest of it follows from group theory. So the same fundamental homomorphism theorem, sorry if you're trying to write that down, but you can, the same fundamental homomorphism theorem works in for rings. The only thing we needed to check is that our isomorphism is a ring map, right? And now you can look at this equation and say that this is an equation about ring homomorphisms, not just group homomorphisms. We'll use this thing the same way. When you want to prove that some factor ring is isomorphic to something, we'll do the checklist. We'll come up with an onto ring homomorphism, check its kernel is the right thing, and then just apply the theorem. All right, let's try it. Got 2 examples. I'll try to write as quick as I can so this video is short, and then we'll call it a lecture. So we know that this isomorphism that you're looking at is true as groups, but I'm claiming as rings, that the ring of integers factored by the ideal of multiples of n is isomorphic to Zn. So here's how we'll do it. Let's define phi from Z to Zn by saying phi of m is the class containing m. We showed that's an onto ring homomorphism with kernel. This was all in the previous lecture. Phi is a ring homomorphism onto Z, n, sorry, I'm trying to write so fast, I'm having a spaz attack here. It's on to Zn, and we've also calculated that its kernel, oops, more spaz attack, its kernel, well, I wrote it as the subgroup generated by n before, but that's precisely the multiples of n. So the first homomorphism theorem for rings says that Z factored by this ideal, this kernel, is in fact isomorphic to Zn as a ring. So that's that factor group Zn that we know. It's also a factor ring. Cool. All right, evidently I left myself enough room that time. Okay, last example. This one's a little meaty, but let's try to get through it, and then we'll call it a lecture here. So the example, the ring I'm going to use was discussed and introduced last time. I'm not going to speak about it much here to keep the video short, but it's the ring of continuous functions on the unit interval under pointwise addition and multiplication. I'm going to let K be the set of functions that are 0 at 1/2. And in the previous lecture, we showed that K is an ideal. And I want to show that the factor ring by K is isomorphic to the field of real numbers. Yeah, so this is kind of interesting because R is not a field, but there's a quotient of it that's a field. R over K is a field. Oh, look at that. I already wrote it. Good. So here we go. How to come up with the phi. I'm just going to do it. This is in practice. You'd have to play around a lot. These things aren't all that obvious, but if I want to show R over K, let me kind of highlight as I'm thinking. I want a homomorphism from the numerator to my target. Yeah, I want a ring homomorphism. So I am going to try to define a function from this ring to R, and I want to do it in such a way that exactly the functions in this set K are sent to the 0 element of R, to the number 0. So I'm trying to, let me just say it out loud. I'm trying to associate to each function a number in such a way that the functions that are 0 at 1/2 get associated to the number 0. I'll bet you can kind of guess what this function phi should do, right? I should just take phi of a function. What number should I assign to it? Well, how about the value of that function at 1/2? Is that what you were thinking? I bet it's what you were thinking. This is a little bit optimistic thinking. I'm not typically an optimistic person, but I can't think of anything else. And let's just hope it works. We have a checklist. We wrote down a function. What's our checklist? Is our function a ring homomorphism? Is our function onto? Does our function have the right kernel? I have a very strong feeling that it's got the right kernel. Okay, let's check it out. So let's take two functions in R, two elements of the ring R. R is a ring of functions. This is pretty cool. Let's see what phi of f plus g is. Well, by definition, it's f plus g's value at 1/2, and by the way we add functions, we take f of 1/2 and add it to g of 1/2. And that's precisely phi of f. Am I going to have enough room? Plus phi of g. So it's additive. Let me start a little further over here. How about phi of f times g? Stop the video and do it yourself. It's f times g at 1/2. This is not function composition. It's pointwise multiplication. So that means f of 1/2 times g of 1/2, and that's phi of f times phi of g. So we have ourselves a ring homomorphism. Step 1, done. Phi is a ring homomorphism. What's step 2? Is it onto? Let alpha be a real number. Ooh, what do I need? I need a continuous function. On the unit interval. Continuous function on the unit interval with f of 1/2 equaling alpha. Well, I mean, we could make life hard on ourselves. We could come up with all kinds of things. We could use linear functions, polynomial functions, exponential functions, lots of continuous functions. I think are candidates here. But this video is getting long. I think I'm going to define, do you have an idea? I'm going to define f on the unit interval. I need its value at a half to be alpha. I'm going to just say that f of anything is alpha. I'm going to take a constant function. What am I doing? Getting tired here, long day. F of anything is alpha. I'm going to take a constant function. Constant functions are continuous. Yeah, no problem. So f is an element of R. Constant functions are continuous. What's phi of f? Well, it's f of 1/2. It's alpha. So onto. Phi is onto. Step 2 is done. Oh, look, I gave myself lots of room. No, this is the last example. Phi is onto. Here I can even make the video a little bit longer here and write it carefully. Phi is onto. Last thing to do is calculate the kernel. Let's say that f is in the kernel. Okay, so phi of f is 0, the additive identity. That means that f of 1/2 is 0. That means that f is in K by definition. So I've shown that the kernel of phi is a subset of K. Half my task. What if we took f in K? Well, that means that f of 1/2 is 0. That means that phi of f is 0. F of 1/2 is phi of f. That means that f is in the kernel. Yeah, so that shows that K is a subset of the kernel. And if we have both of those things, K is a subset of the kernel and kernel is a subset of K, then we know that the kernel is equal to K. So I'll end this just by drawing the picture. We took the ring of continuous functions on the unit interval, which, by the way, in books is typically denoted by this. C01, ring of continuous functions on the unit interval. I like that notation better than R. What is R? I have to remember what R is, but I don't have to remember what this is. It almost tells me what its name is. And we took that R and we mapped it to the real numbers by sending a function to its value at 1/2. 1/2 wasn't arbitrary because that made R over K, those functions that vanish over half, it made K its kernel. And so the fundamental homomorphism theorem says that the function psi that sends a coset to whatever any representative's value at a half is, that's a ring isomorphism. Cool. So I will end this long video just by kind of saying out loud one more sort of way to interpret what we just did. If you're considering functions, continuous functions, but you're only going to consider them modulo the functions that vanish at 1/2, functions that send 1/2 to 0. So what that means is that you can't tell the difference between two functions if they have the same value at 1/2. Well, then what can you tell? What's left when that's over? Well, the value at 1/2. That's all you know. So the real numbers. So that quotient ring, the residue that's left over after you only are considering functions' values at 1/2 is what their value is at 1/2. And that is just a number. And that quotient ring is isomorphic to the field of real numbers under that correspondence. Okay, thanks for listening.